Welcome. In this video, I'm going to explain how to get the Pythagorean theorem from scratch. If you've ever wanted to understand why the Pythagorean theorem is true, you'll learn it in this video. The Pythagorean theorem shows the relationship between the sides of a right triangle. Specifically, the Pythagorean theorem states for any right triangle that the sum of the square of the two short sides equals the square of the long side. Said another way, a squared plus b squared equals c squared. Here we have a right triangle in brown. This triangle will remain the same color throughout this presentation. It doesn't matter which right triangle we draw, we only care that A and B are perpendicular to each other. That is, they are 90 degrees to each other. Other than that, the lengths of sides A and B can be whatever we choose. The long side connecting sides A and B together at the far ends is the hypotenuse, side C. The length of C is fixed by whatever we choose A and B to be. That is, C squared is exactly and always equal to A squared plus B squared. If we were to start randomly performing operations on these sides in the hopes of finding a relationship that we can trust, we might dream up different formulas like A times B equals B plus C, or a host of many other possibilities. All of these would likely be incorrect. However, we might just be lucky and stumble on the correct formula shown. If we did, we would say, cool, that worked. But this wouldn't help us understand why it was true. As often happens, we have to approach problems in a non-intuitive fashion. What we need to do rather than take guesses about possible relationships is to start with what we know. First, let's understand what the Pythagorean theorem means. This part won't show you why it's true, but it will show you what it means. We'll get to the why very shortly. Recall in our triangle, the hypotenuse is side C. Let's make a square from this side by drawing another line of length C perpendicular to it. This will give us a square with an area of C squared. We follow the same procedure with sides A and B. Side A will make a square with an area of A squared, and side B will make a square with an area of B squared. These squares just produced are placed in green at the bottom. We can see that the Pythagorean theorem tells us that the sum of these areas made from the short sides is equal to the area made from the long side. The original right triangle showed a relationship of lengths. However, the quantitative relationship between the sides is given as area, not as lengths. While it seems amazing, this is true for all right triangles. In this presentation, I'm going to show you why this is true using only concepts that you are probably already familiar with. Before we start, we need to show a few basic ideas that we'll rely on to produce the Pythagorean theorem, and that aren't difficult to understand. Here are shown two triangles that are exact copies of each other. One I've labeled triangle 1, and the other I've labeled triangle 2 for convenience. Since these are exact copies, all the sides are the same, and all the angles are the same. That is, for example, angle B of the first triangle is the same as angle B of the second triangle. Now, what do we need to know to make sure these are equal when I've not told you they are exact copies? Let's recall all of the angles of a triangle add up to 180 degrees. Thus, any two angles in a triangle determines the third angle. We don't need to know all three. We only need to know two, and then we can always calculate the third angle. Thus, when two triangles have two angles that are the same, then the third angle of both triangles must be the same. However, it is possible, even when all the angles are the same between two triangles, that the triangles are not exact copies. Compare the green triangle to the other triangles. The angles are the same between the green and the light brown triangles, but the sides are all double. Thus, we also need to know that one side has the same length in both triangles, and that this side is between the two angles that are the same in both triangles. For example, if we know angles A and B are the same for the two brown triangles as shown, and side C is the same for the two triangles, then those two triangles must be exactly equal to each other. Specifically, we can know that triangle 2 is an exact copy of triangle 1 if we already know that angle B of triangles 1 and 2 are the same, that angle A of triangles 1 and 2 are the same, and that side C of triangles 1 and 2 are the same. We don't have to know beforehand that sides A and B are the same, or even that triangle 2 is a right triangle. The second piece of information we need is that the angle of a straight line is 180 degrees. Regardless of how we take scissors and cut this angle up, all the pieces still add up to 180 degrees, half of a circle. The sum of the parts is equal to the whole. When we cut an angle of a line in half, the angle is called perpendicular, which means 90 degrees. It represents 1/4 of a circle. The last thing we need to understand is the area of a right triangle. Most of us probably already know that the area of a rectangle with sides A and B is A times B, shown in green text. When we cut the rectangle in half, as shown on the bottom, then we have half of that area cut into two equal pieces. Therefore, the area of the purple triangle is 1/2 A times B. That's all we need. We can now produce the Pythagorean theorem from scratch. We start with a triangle we showed earlier. Side C is highlighted with a black line. Now, make an exact copy of that line as shown directly above. Now rotate that exact copy exactly 90 degrees as shown. Do this again to make a square on top of the hypotenuse as we did earlier. Obviously, the area of that square is C times C. Now, let's make a line along the two short sides of our triangle as shown in red. Let's draw two more lines perpendicular to each of the new red lines we drew. We are forcing these blue lines to be perpendicular to the red lines. That is, the blue lines are turned exactly 90 degrees to the red lines. Thus, we know we have 90 degrees angles where the blue and the red lines meet. This forces the intersection of the two blue lines to also be 90 degrees. This completes our diagram. Now we'll use reason to fill in the rest. Recall that a straight line is 180 degrees. Recall also that the angles in a triangle add to 180 degrees. The olive green box shows the sum of the angles of the brown triangle as 180 degrees. That is, angle A plus angle B plus 90 degrees equals 180 degrees. The orange box shows the sum of the angles for the straight line as 180 degrees. That is, unknown angle plus angle B plus 90 degrees equals 180 degrees. Thus, by comparing the orange and olive green boxes, we can see that the unknown angle in the orange box is simply angle A. That is the only way they can add to 180 degrees. Now, let's examine the sum of the angles for the original triangle in the olive green box with the triangle shown by the blue arrow and shaded in light blue. By comparing the equation in the green box, angle A plus angle B plus 90 degrees equals 180 degrees. With the equation in the blue box, angle A plus unknown angle plus 90 degrees equals 180 degrees, we can see that the unknown angle must be angle B, because that is the only way they can sum to 180 degrees. Now we can see the light brown triangle and the light blue triangle are exact copies of each other. Angle A of the shaded triangle and angle B of the shaded triangles are the same, and both have a side of length C between those angles. Since these triangles are exact copies of each other, everything about them is the same. In particular, the sides opposite angle A have length A, and the sides opposite angle B have length B, as shown. Now we have the exact same situation with the straight line as just discussed. By comparing the sum of the angles for the triangle in the olive green box with the sum of the angles in the orange box, we can see the unknown angle must be angle A once again. This figure shows the completed diagram with all of the angles and sides for the triangles using this process in repetition. We see that the 4 triangles around the green square in the middle, see the red numbers, are all exactly equal to each other. Thus, the big square is composed of 4 triangles and a square in the middle. The big square has sides with a length of A plus B, as shown. The figure has been simplified and is shown in the top right corner. We'll calculate the area of the big square 2 different ways. First, let's calculate the area of triangle 1. Area equals 1/2 A times B. If you forgot why, please review the earlier part of this video. The area of all 4 triangles taken together is 4 times 1/2 A times B, which is 2 times A times B, as shown in red text. The small inner green square has an area of C squared and is shown in green text. The area of the big square is shown in purple text. The big square is composed of the 4 triangles and the green square, which makes an area of 2AB plus C squared. We can also calculate the area of the big square by its sides as shown above. Basically, the big square area equals parentheses A plus B and parentheses times parentheses A plus B and parentheses, which is A squared plus B squared plus 2AB in expanded form, as shown at the bottom in purple text. We have 2 formulas for the area of the big square. Using one of the ways, we see that the big square has an area of A squared plus B squared plus 2AB. Using the other way, we see the area is 2AB plus C squared. These 2 calculations represent the same big square. Obviously, the area of the big square equals itself. When we simply write this idea down, A squared plus B squared plus 2AB equals 2AB plus C squared, we can easily see 2AB on both sides of the equal sign. These cancel each other. That which remains is A squared plus B squared equals C squared. This is the Pythagorean theorem itself. Thus, we have shown from scratch the Pythagorean theorem, and we're done. Visit our website if you would like to learn more. Thank you.